Before I go into the details of the talk, I will first introduce you to the highlights. So in this paper, we introduced a new scalable variation of coordinate descent, which is very well suited for running on the cloud. And as I will show, this algorithm will have exactly the same convergence behavior as a single machine, single-threaded coordinate descent algorithm, while providing a near-linear scale-out and speedup. Okay, let's start with the problem definition. I will deal with a standard supervised prediction problem. So we have a set of training examples. Every training example consists of a feature vector and a label. And this talk will be about linear models. So we are trying to find model parameters for every feature such that the dot product between the model parameters and the feature vector explains the target as best as possible. And the goal of learning is to find the model parameters that are as close as possible. Okay, to go a bit more into details about the problems that we are dealing with. So we are dealing with very large-scale data. So we are assuming we have billions of features and tens or hundreds of billions of training examples. I will show you later also some examples with up to 1 trillion training examples. In addition, so typically if we deal with a lot of features, the data has a lot of sparsity because having many features usually comes from things like categorical variables, like video IDs and so on, that create a very large number of features and also creates through one hot encoding a very huge sparsity. So this is a very typical pattern. So think of, for example, of variables like country, gender, video ID, and these variables create a large sparsity and also create very large feature vectors. And the sparsity is something that we will use later to make the algorithm very scalable. So after introducing the machine learning part, now let's talk about the system environment that we are dealing with. So we specifically want to run this algorithm on a cloud environment. That means for every physical machine, there are many virtual machines on it. And we also want to especially deal with preemptible VMs. So these are typically the lowest cost VMs that you can obtain. So they are much cheaper than normal VMs. And these are VMs with lower guarantees. So these are VMs that can be preempted for higher priority jobs, for example. And the goals that we have for our algorithm are the following. So we want to have a robust distribution. That means the algorithm should be deterministic no matter of how many machines we are running it on, and also no matter how the computing environment behaves. So if our machines are preempted and so on, we don't want to see any effect on the algorithm. And secondly, what we want to have is a linear scale out and speed up. That means the more machines we have, we can either run much larger problems, or we can run the problem with the same size much faster. Okay, after you've seen the problem definition, let's have a look at the learning algorithm. So before we talk about distributed algorithms, let's step back and think first about popular single machine algorithms. And there are basically, I think, two big families of optimization algorithms out there, which are simple to implement and are popular to choose for implementing single machine algorithms. And one of them is stochastic gradient descent, which goes an example at a time, computes gradients, updates the model parameters, and goes to another example. And the other kind of family are coordinate descent algorithms, where you go, instead of example at a time, you go feature at a time. So you look at one feature, compute the sufficient statistics, update the model parameter for this feature, and move to another coordinate. Okay, I will talk now more about coordinate descent because this is the algorithm that we will make at the end scalable. So if you think of it, as I explained before, coordinate descent is quite hard to parallelize because it's a very sequential algorithm, and in every step of the algorithm there's not much work to do. So if you think of in a sparse data set, if you look at one feature, and computing the sufficient statistics is very fast for this particular feature because you only have to go to the examples that are non-zero. So there's not much work to be done. And if you don't have much work to do, then it doesn't make sense to use many machines for doing little work. And basically, this algorithm is hard to distribute without making sacrifices. So the key idea of our scalable variation of coordinate descent is the following. So we are trying to use the structure and the sparsity. So the idea is to partition the features that we have into what we call a pure block. And these are groups of features such that every training example has at most one non-zero element in this block. I will show this on the next slide on an illustration, and it gets a bit, I think, more clear. And the nice thing is, then we can update all the features in a block in parallel at once. And one can show that this is the same thing as updating one feature at a time. So this property means we are not losing anything compared to a single-threaded standard coordinate descent algorithm. And the upshot of it is actually that now we have a reasonable amount of work to do before we go to the next part of the computation. So, and if we have a reasonable amount of work to do, that means we can benefit from having several machines. So this is the algorithm in, again, the same algorithm, but now illustrated on some graphs. So here you see a design matrix, the same one I showed you in the beginning. And this one is separated into 3 blocks. And if you look at each of these blocks and at each example, you see that for every block and every example, there's only one gray cell per example. And this gray cell is the non-zero feature. And obviously, dealing or updating or computing sufficient statistics for features within a block is the same, and updating them at the same time is the same as doing this in sequence, because the sufficient statistics for every feature is independent of the sufficient statistics of the other features. So also the updates will be independent. That means running them in sequence or in parallel will give you the same result. So this is the basic idea of the algorithm. And now let's have a look how we can distribute this. So the idea is still we go one block at a time. So it's the distribution is not done over blocks, but the distribution is done over examples. So we shard the examples into several example shards, and the sufficient statistics of the examples are computed in a distributed way. And I will show you some illustration of this in the next slide. And the nice thing about this is the distributed algorithm does now exactly the same thing as a single machine algorithm, which in turn does the same thing as a normal coordinate descent algorithm. So we have an algorithm that is scalable, but does the same thing as its single machine variant. Okay, I will illustrate this now on an example that you see the whole flow of the system. So here again is the data that we've seen before. We have our design matrix. We have the model parameters that we want to learn on the design matrix. And we have predictions. So this is basically the vector product between the model parameters and the training data. And we have now our distributed environment. So we have a master that coordinates everything. And we have a set of workers. Here for simplicity, I show 2 workers. So the flow is the following. So we will first, or the master selects first a block that the algorithm should work on. So then we can forget all the rest of the data. So we can just have a look at this particular block. And every block, as I told you before, is sharded into groups of examples. And the first thing that we need to do is compute sufficient statistics for coordinate descent algorithm. So in this case, the workers will pull the shards and compute the sufficient statistic for their subshard that they are responsible for. And sufficient statistics of coordinate descent are sums, so they basically compute partial sums, and the partial sums for the examples that they are responsible for. Okay, after the workers have collected the sufficient statistics for the shards, There's a distributed aggregation phase where all the sufficient statistics are aggregated and summed up and sent to the master. After the master has the sufficient statistic, it can update the model parameters. This is just the standard coordinate descent update rules. And after they are updated, we can actually update the predictions. So as I told you in the beginning, these predictions are basically the or the matrix vector product between model parameters and the design matrix. And this is something in standard coordinate descent algorithms as well, something you have to carry around always. And as soon as you update your model, also these predictions will change. So you have to make some delta operations to bring these predictions up to the new model. And again, this is done over the workers. Okay, so this is basically the whole distributed flow that I was talking about. So for every iteration, the master selects a block. Then the workers compute sufficient statistics, aggregate the sufficient statistics. The master can then update the model parameters, and the workers update their predictions. And yeah, so this is the basic flow, and then the system goes to another block until it converts. And as you can see here, the workers are doing all the heavy lifting. So everything that is depending on the training example is executed on the workers. So this part will scale well. And all the other parts, like selecting a block and update the model parameters, is executed on the master. So I have here some runtimes for a data set with about 20 billion training examples and 20 workers, just that you have an idea how the runtimes are for these phases. And as you can see, as I said, everything that's computational intensive, like computing the sufficient statistics and updating the prediction, is done by the workers, and everything that's cheap is done by the master. I want to especially highlight here that this is a sequential algorithm. So you see here, all of these steps are fully sequential, so there are barriers between all these steps. And as you can see, each of these steps is pretty fast, so in the order of a few seconds. So if you try to implement this, you will see some challenges. So the first one is, as I said, you have a sequential algorithm with short barriers. That means as soon as in your system something happening, some operations take a bit longer, and there will be operations that take a bit longer as soon as you scale out, then you have a problem with stragglers. And this is a pretty challenging problem if we are dealing with hundreds of machines, especially if you're dealing with low priority VMs and so on. And the paper talks about several solutions or how we try to address these problems. So one of them is we are using dynamic load balancing between all the machines. We overshot the problem, and we try to avoid the distributed file system as much as possible by using caching and prefetching and so on. So the biggest stragglers are actually from the distributed file system. And the second kind of challenge that we have is that in this problem that I showed before, we have some state that we have to keep up to date, and these are these predictions. And this is a pretty large scale, pretty large state if we're dealing with a lot of examples. It's for every training examples we have one float. So if you think of 1 billion training examples, we have about 4 GB of state that we carry around. If we have 1 trillion training examples, we have 4 TB of state. And this is a state that changes every few seconds. So we have to keep it. In sync. We are not allowed to lose it and all these things. And that's also somehow challenging if you are dealing with like low priority cloud environment. Okay, so finally I want to show you some experiments. So as I told you, the goal of the work is to get an algorithm that has a linear or near linear scale out and speed up. And here's an example of scale out. So what you see here in this graph is on the x-axis you see the scale of the problem. So on the leftmost side you see the 1x scale. We have 20 billion training examples and 20 workers. And then we increase the number of training examples and the number of workers by the same factor. up to 50x. So this corresponds to 1 trillion training examples and 1,000 workers. Every worker has about 8 CPUs, so this will be about 8,000 CPUs. And what you see there, the red curve is the time for full iteration, and the other 3 colors show you the other subphases of an iteration. And as you can see, the time for the 1x problem is about 14 seconds, and going up to 50x of this scale increases a bit the time, but not too drastically. It's about 19 seconds. So it's a pretty linear scale up to a pretty large problems, like 1 trillion training examples and 1,000 workers. Okay, so the other thing we were interested in is to get a linear speedup. And in this experiment, we keep the number of training examples fixed, so the problem size stays constant, and we vary the number of workers. So what you see here on the graph on the top left-hand side is the runtime for 1 iteration with 1 worker. And if we extrapolate this, so assuming we get a linear speedup, then you would get this green line. So if you have 100 times more workers, you would assume that the runtime drops from about 500 seconds to 5 seconds. So this would be the optimal linear speedup. And what you see here with the red curve is the actually measured speedup. So we double the number of workers and measure how long it takes. And the interesting thing here is what you see is that we actually get in the beginning a superlinear speedup. So that's somehow surprising, because one would think the theoretical limit is to get a linear speedup. But the interesting part is here that actually, if you increase the number of workers, you increase the number of memory in your system. So if you have only 1 worker, then you have, in this case, 30 gig of memory. If you have 2 workers, you have 60 gigabyte of memories. And if you have 100 worker, you have 3 terabyte of memory. And so the more memory you have, the more things you can cache, actually, and the less access to the distributed file system. So it makes somehow sense that in the beginning, increasing the number of workers actually can give you a nonlinear speedup. And we also say it slowly plateaus, and the benefit goes away when we have more and more workers. And there the reason is, so the more workers you have, the faster you iterate, and the more or the stronger become the straggler effects. So in this case, if we look at the 128 workers, we have iterations that are less than 5 seconds. And in these 5 seconds, there are several sequential steps, and having barriers every second is very hard to enforce over hundreds of machines. So the really interesting thing, I think, about Speedup, if you think it from another angle, is so basically when you're running a machine learning algorithm, you want to have the result as fast as possible, and you want to pay as little as possible. And a linear speedup actually means that the costs are constant, and you can just decide how fast you want to have the results. So this would be a perfect linear speedup. It would mean if you run your algorithm, or if you want to have the results in 10 hours or 1 hour, you pay the same price. Actually, in practice, we have seen that speedup is not exactly linear. And so actually, in this case, what the figure shows you is we have the time to converge in hours on the x-axis, and the cost if you run this in a typical cloud on the y-axis. And there you can see, in this case, actually, you can get results faster and cheaper. So this is the explanation of the curve that you have seen in the last slide. Okay, so to conclude, so what I've presented today here is a scalable variant of coordinate descent, which is robust regardless of the scale out and the computing environment. We have shown that this fits very well to a standard cloud environment, and have shown on experiments that we could run in preemptible cloud, so on very low-cost environments, scaling to thousands of cores, and can solve problems with up to 1 trillion training examples. Okay, thank you.
Questions?
I have a question because so each worker has some state, and if a machine fails, state is lost. Do you duplicate workers or what you do? It's the first question. The second question is, you have 1,000 machines, and you still have one master. Don't you have network problems when aggregating?
Okay, so for the first question was about. So let me answer the second question first. So the problem with the aggregation. So we have shown an algorithm that actually is independent of the number of workers. So it's a worker-to-worker shuffle, and the amount that flow. So the in and outflow of each worker is constant, no matter how many workers you're running it with. Also the number or the amount of data flowing into the master is constant, no matter how many workers are there. So it's described in the paper. And to the first question, this was about machine failures, exactly. So so actually the cloud providers usually give you a grace period on preemptions. So for normal preemptions, which can happen much more often, you have a grace period, and if you manage to evict all the state that you have or move to the state to another worker, you don't lose anything. And on hard machine failures, these are much rarer. In this case, we have a special recovery phase, okay, which is also a part of the measurements that we have.
Okay. Okay. This gentleman first.
I had just a couple of quick questions. The first one was, what's the recommended way to come up with the blocks such that there is like at most one?
Yeah, that's a good question. So so typically, actually, structure is already given to you, because typically the design matrix is not something that's given. That's something you construct yourself, and you typically create it from underlying variables, like from categorical variables, and you can use exactly this structure. Like one block is one variable. That's a typical way to get a very good structure.
Mm-hmm. Thank you. And the second quick question was, how well do you think this would do for the factorization machine setting?
So this work is only about linear models.
Okay. All right. Thank you.
For problems where you might want to correct your learning later based on spam or late arriving data, is it harder to do that in the coordinate descent setting than in the stochastic gradient setting?
So what was the first part? Sorry.
In scenarios where you might want to have corrections to your learning, it's online learning, right? So,
okay.
Like it's a real-world scenario, so you might have spam or late arriving data, and okay, is it harder to do that correction in a coordinate descent setting than in the stochastic gradient setting where you're doing example at a time?
Yeah. So this is a batch learning algorithm, so it's not an online training where you only go once over the data. But what you can do is, you can, as soon as you have new data, you can just include it in your cycle. So in some sense, you keep on iterating. You just move the window over which data you're iterating.
Okay, the last one. Last one.
Great talk. I was wondering if you could give any intuition about what type of problems you're seeing success with this on, because I think one of the striking things is it's a very simple approach, but scaled out to huge size. Are you seeing this being competitive with more exotic models such as deep learning?
Yeah, that's a good question. So I think, so basically the model has to be well suited for a coordinate descent algorithm. So I think that's the. So if you wouldn't implement it with in a single machine with a coordinate descent algorithm, then I guess you have some reasons why you wouldn't choose coordinate descent. But if you would do it, then there might be it might be reasonable also to use this kind of algorithm.
Okay. Let's thank the speaker again. Oh, by the way, so what's the feature dimension of the data?
The feature dimension?
Yes, you just told us that 20 billion samples, but what's the feature dimension?
Okay, so for the experiments, this was a few billion, a few billion features. I don't know, 2 billion or something like this.
Okay.
It's in the paper.
Okay, let's thank the speaker again.